All right, folks, so I'm recording the session. As promised. So you guys can see my screen. As I told you in my message, if you scroll down and you go to the project submission session, I updated this file here for the project. Okay, so please take a look at it. And for the exam review, which is today, I placed the link for the Teams, this meeting. I'm going to place the full recording, the complete recording here too, as soon as we're done. So you're going to see the link to the full recording here. And please download the updated slides for the review session. I updated the slides just yesterday. So, and it has some new information. So please download the set of files. Also, I sent a message a few days ago. I also updated this file here. Advanced Econometrics Week 1 lecture, non-stationarity and unit root and contegration. Just one second here. So I included 2 new slides in this file here. So if you haven't yet downloaded the new version, so please download it and I didn't change any information. I just added more information on unit roots and contegration. What else? Yeah, I made some small changes in the time series file, but it's nothing important. It's just to make some things easier for you, so you can see version 2 now. But no big deal. It doesn't matter much. I guess that's it. Let's see what else. Any updates here? Yeah, I think that's it. I think we can start. Look, your microphones are turned off. You cannot use your microphones. You cannot use your camera. So if you want to ask me a question, you need to type your question in the chat. I have a second screen open because my computer has 2 screens. So on the second screen, I have the chat open. So if you want to ask something, you can do so immediately. Just type in the chat. Again, you cannot use your microphone and you cannot use your cameras. So if you want to ask me something, just use the chat. All right. And you can ask me a question at any time. Okay. Because you can see my screen here, but I have this other screen where I have the chat open, so I can see whatever you type in. So if you want if you want me to clarify something, then just type in the chat. All right. You can do it at any time. All right. So let's begin with the review. I cannot finish this in 1 hour. So as I told you, in the timetable, the slot is for 1 hour, but I'm gonna probably finish at 12 at noon. So if you have to leave early, no problem. You can just leave the Teams room. I'm gonna keep going, and I'm gonna record everything and place the recording later on Moodle. So no problem if you have to leave at 11. But I will just keep going until probably noon. All right. I can. It's impossible to finish this in just 1 hour. All right. So let's see. The contents for today are: first, I'm going to discuss with you the difference between exogenous and endogenous regressors. Then I'm going to go over and compare the different data sets that we can have. I'm going to do that very quickly. Cross-section, time series, and panel data. This is just a brief review. And then finally, I'm going to compare all the time series and panel data models that we have seen in this module. Okay, so I'm going to do a comparison across all models that we have seen. But first, I'm going to begin with a discussion about the nature of the regressors, okay, and then the nature of the data. All right, so step 1, let's have a brief discussion about the nature of the regressors. What is the difference when you have an endogenous regressor or when you have an exogenous regressor? Or, there are other types too, like control variables, strictly exogenous regressors, and so forth. So remember this, that econometrics serves two main objectives. The first one, of course, is prediction or forecasting. So whenever you hear about prediction, we are talking about forecasting. In this case, the regressors do not need to be exogenous, but if your objective is to establish causality, then the regressors, they need to be exogenous at least, but actually in most cases, the regressors, they have to be strictly exogenous. I'm going to define what is the difference between exogenous and strictly exogenous. So just remember this: if you're doing forecasting, you don't have to worry about the exogeneity of the variables, but to establish causality, you do need the variables to be ideally strictly exogenous. Okay. And as I mentioned this in class many times over, identifying causality is way, way more difficult than forecasting. Okay, it's much more difficult to do causality analysis than to do forecasting. But it depends. Maybe, when you work, when you have a job, they ask you to do forecasting. They don't care about causality. That's fine. That's fine. You can use econometrics in either way. The thing I think it's much easier to do forecasting because you don't have to worry at all about the nature of the regressors, if they are exogenous or not. You don't have to worry about instrumental variables. So let's see each single type of regressor. The first type is the endogenous regressor. And the endogenous regressor has the endogeneity problem, okay? And the endogeneity problem is the same as the simultaneity problem. It means that the endogenous regressor is correlated with the error term, okay? So if any of the regressors is correlated with the error term, which means if there is a non-zero covariance between the error term and the regressor, that regressor is endogenous, okay? And that means when the error term is correlated with the regressor, that means that you have reverse causality, okay? That means you have a reverse causality. And reverse causality means it goes from the dependent variable to the regressor. Because when you write a regression function, it's a function. So causality ideally goes from the regressor to the dependent variable. That's why the dependent variable is called the dependent variable. So you're trying to establish causality that goes from the arguments of the function to the function, all right, from x to y. So it should go from the regressor to the dependent variable. But if the regressor is correlated with the error term, and the error term is directly correlated with the dependent variable, that means you have reverse causality. Then the function is affecting its own argument, okay? Then the dependent variable determines the endogenous regressor. And that's a big problem. That's the biggest problem that you can have in econometrics. It happens all the time, especially at the macroeconomic level. If you're doing macro econometrics, you're going to have reverse causality all the time. And the problem is endogeneity causes the worst kind of problem that you can have in econometrics. Okay, the coefficients on the endogenous regressors are going to be inconsistent. And remember, inconsistency is the worst type of problem that you can have. It's the worst type of problem that you can have in econometrics, because inconsistency means you have a bias in your estimates, and the bias will not disappear even if you increase the sample size. So when I say that the coefficients are biased, even asymptotically means even if the sample size grows to infinity. Even if you have a very, very, very large sample size, that means asymptotically, as n approaches infinity, n is the sample size, the bias in the coefficients in the estimators will not disappear. This is the worst type of problem that you can have in econometrics. Because if you say, okay, my estimators are biased, that's a problem. But if the bias is not asymptotic, it means that the bias that you have is caused by a, let's say, small sample size. But if you have more data, if you have a bigger sample, then the bias will disappear. So in that case, you can have a biased estimator, which is still consistent. Okay, it's possible to have a biased estimator that is still consistent. Okay, and in machine learning, you get that. For example, when you try to do forecasting, a prediction, many models for forecasting, they are actually biased. But when you have more data, the bias disappears. So it can be biased, but still consistent. Okay, an estimator can be biased, but it's still consistent. So the bias disappears asymptotically. But when you have endogeneity problems like reverse causality, then the problem cannot be solved just by adding more data, because the bias is asymptotic. And that means the estimator is inconsistent, okay? Even with more data, you're not going to make the bias disappear. So if you want to identify causality from an endogenous regressor, then you must use instrumental variables like two-stage least squares and GMM, okay? You can ask, but if I have an endogeneity problem, I just delete the endogenous variable from the regression. Actually, you cannot do that, because ideally, you are trying to establish causality from that regressor, okay? Because that's the question that you're asking. You're trying to establish causality from that regressor, but that regressor that you're trying to establish causality about is actually endogenous. So you cannot just delete it from the regression. You have to use instrumental variables, either using two-stage least squares or GMM. The next type of regressor is the exogenous regressor. It's also known as a predetermined regressor. It is orthogonal or independent to the present and past realizations of the error term. Remember, for a regressor to be exogenous, it needs to be orthogonal to the error term. If it is orthogonal to the present and past occurrences of the error term, then it's exogenous. But it's an exogenous regressor, but it's still correlated to future realizations of the error term. And you say, okay, but why does the future matter? Well, the future matters, especially in economics, because most things in economics are driven by expectations about the future. So most, especially in time series, like most variables, they will never be orthogonal to the future error term, because expectations matter. So remember this, when I say an exogenous regressor, it means it's exogenous relative to the present and the past, but it's not necessarily exogenous relative to the future. If you have a strictly exogenous regressor, then it's orthogonal. Orthogonal means independent, okay? It's orthogonal to the present, the past, and the future realizations of the error term, okay? So it's a much stronger type of exogenous regressor. It's the best. Ideally, that's the best type of regressor that you can have, okay? If you could easily find a regressor that is strictly exogenous, you're good to go. The problem is that in practice, good luck. It's almost, especially in time series macro econometrics, it's basically impossible. It's almost impossible to find strictly exogenous regressors, okay? So yeah, I'm gonna talk more about this later, but in practice, it's very difficult to find at the macroeconomic level. So so that's why most empirical work now is done at the micro level, because at the micro level, you can say that certain variables are strictly exogenous from the microeconomic perspective. But at the macro level, very difficult. The other type of regressor is we have the control variables. Usually they are not exogenous, okay, but they are included in the regression just to control for extra effects that you want to control, whatever, the age, level of education, postcode, demographic data, and so forth. But remember, because they are usually not exogenous, the coefficients, the estimates that you get on these control variables, they do not have causal interpretation. You cannot assign to them any causality, okay? You can only, remember the rule, you can only assign causality to a variable that is ideally strictly exogenous, okay? Control variables most of the time are gonna be endogenous. You can still add them to the regression equation to control for those effects, but just remember the estimates that you get from them do not have, you cannot imply any causality from those estimates. They're just there to control for those effects. The last type of regressor is the instrumental variable. And the instrumental variable needs to be highly correlated with the endogenous regressor. And the instrumental variable must affect the dependent variable on the left-hand side only indirectly, okay, through the endogenous regressor. So remember, the instrumental variable cannot have a direct effect on Y. It can only have an indirect effect on Y through the endogenous regressor, okay? And so it must be highly correlated with the endogenous regressor on the right-hand side, and it must not be correlated with the, well, in practice, there's gonna be a little correlation. But the thing is, because the correlation goes through the regressor, the point is, when you include the instrumental variable needs to affect the dependent variable only indirectly through the endogenous regressor, okay? So you can find a little bit of correlation with the dependent variable, but the effect is always indirect through the endogenous regressor. So because if the instrumental variable affects the dependent variable directly, then it's not an instrumental variable, okay? And it should be added to the regression as one more regressor, okay? Anything that affects Y directly should be included as a regressor, okay? And of course, the instrumental variable needs to be exogenous or orthogonal to the error term in the main regression, okay? So yes, the instrumental variable has to be exogenous. Ideally, it needs to be a strictly exogenous. The more exogenous it is, the better for you. And basically, in practice, what the instrumental variable is going to do, it's going to split the endogenous regressor in two components. Okay, I explained this in class. Basically, you have this endogenous regressor, but the endogenous regressor has two components. It has the endogenous effect and the exogenous effect. What the instrumental variable is going to do is to divide the endogenous regressor that you keep in the regression. Okay, your endogenous regressor is still in the regression, but you're going to split its effect into two components. The first component is the endogenous component. Okay, and this endogenous component is the component that creates the inconsistency in the estimates. Remember that I told you that if you have an endogeneity problem, it creates inconsistency. Okay, inconsistency means asymptotic bias. Inconsistency means asymptotic bias. So the endogenous component is what creates this asymptotic bias. Now, but there's a second component, and this is the component that you're interested in. The endogenous regressor has an exogenous component, and that exogenous component of the endogenous regressor is what you're looking for. That's the component that contains the causal effect. Okay, so remember this. You have an endogenous regressor, so you have an endogeneity problem. It creates inconsistency. It creates this asymptotic bias. But the endogenous regressor has two components. It has the endogenous component, which creates the inconsistency, but it also has an exogenous component, and that's what you're looking for. That's the causal effect. So when we use the instrumental variable, what the instrumental variable is going to do is to purge the first component, which is the endogenous component. So the instrumental variable purges the endogenous component, and tries to eliminate the inconsistency, and it keeps in the regression only the second component, which is the exogenous component, which contains the causal effect. Okay, so that's basically what the instrumental variable is doing for you. It's identifying causality from an endogenous regressor, because initially, because the regressor is endogenous, the estimate from that regressor does not have a causal interpretation. So if you want to identify causality from an endogenous regressor, you have to purge the endogenous component, and then you remain only with the exogenous component, and then you can identify causality. Okay? All right, so now quickly, let's see the different data sets that we can have. The first type is the first thing that you learn in any econometrics course. It's cross-sectional data. Now we have different variables on different entities. Remember, when I say individuals, I mean entities or groups. Okay, different textbooks are going to use a different language. So if I say groups, entities, or individuals, I mean the same. These are just the cross sections. Okay. And by the way, some textbooks they say cross section instead of individuals. So if you hear words in panel data models like individuals, groups, entities, or cross section, they mean the same. Okay. But remember, the cross-sectional data is just for one time period. Okay, you only have one time period, which could be 1 day, 1 hour, 1 year, and so forth. It is displayed like this, so you can have, for example, this is country level data. You can have different countries, and then you have different variables for each country, like GDP and so forth, consumption, income distribution, and so forth. You can have many variables on many countries for the same year. Okay, so those observations are just for one year in specific, in particular. When we go to time series, it's just the opposite. We have just one individual or one country or one group or one cross-section. It's just one cross-section. We have many variables, and the many variables are displayed over time. We have spent a lot of time with this. So this is just one entity. In this case, it's Puerto Rico. By the way, a very nice island. I have been there like 5 times already in the past. So you have different years for the same cross-section. You have different variables. It's just the opposite of the cross-section data set. You can pull many different cross-sections over time. Okay, so if you have independent cross-sections over time, you don't have yet panel data because they're independent cross-sections. So the data now is displayed over time, but they are not controlled for the same individuals. Okay, so just because you have cross-sections over time, it does not imply that you have panel data. Okay, because if you look at the data set on the screen, for example, you're not controlling for the individual. So you don't know who the individuals are. Okay, you don't know what the units are. You don't know if you're observing the same units over time. So in this case, you're just pooling the data. You have a pooled cross-section or pooled data. You're just stacking. When I say pooled, I mean to stack. You're just stacking the data, and you're not controlling for the individual. So for you to have panel data, you need to follow and collect data on the same units over time. Okay, if you don't know who the units are, if they change over time, then you don't have panel data. You're just pulling or stacking the data. So this is stacked data. Officially, it's called pooled cross-section. Pooling means stacking. In order for you to have panel data, you need cross-sectional data over time for the same individuals. Okay, so the same cross-sectional units, the same entities, the same individuals, they must be followed over time, like this. So now observe that you have the second column here, city. So this is city level data. So the second column here controls for the the cross-sectional units. And that's the second column here is what gives you the panel data characteristic of this data set, okay? Because you have different variables here, the columns. They're spread over different years, but you are also controlling for the same units. You're basically following the same units over time. In this case, the cities. So here you have panel data, okay? Now, moving on. Folks, remember, if you want to stop me, if you want to ask a question, just type your question in the chat. Any clarifications and so forth. So now let's compare the different time series models, okay? So I'm going to begin just by refreshing your memories about the steps that you have to follow always when you're modeling time series, okay? So the first step is that you need to test each time series individually for unit roots, okay? So even if you're gonna have a model with like lots of time series, you need to test them individually one by one, okay? Because you need to know which ones have a unit root, which ones are trans-stationary, and which ones are already stationary in levels, okay? So the first thing that you do, each time series must be tested individually for unit roots, okay? And when a time series has a unit root, it's called an integrated process, okay? So an integrated process means the series has a unit root, and you must check that for every single series individually. Then the second step, using the unit root tests, is to identify the nature of the time series, okay? Basically, we have three options. The time series could be individually, okay? This applies individually. The time series could be stationary, so we say I0 in levels. So in this case, the series has no trend, no time trend, and no stochastic trend either, okay? Because remember, you can have the two types of trends. You can have time trends, which is usually a linear time trend, but you also have that kind of erratic trend, which is the most difficult part to forecast in time series, which is the stochastic trend. But when the series is stationary in levels, it does not have either one of them. It does not have a time trend, and it does not have a stochastic trend. The second option is that the time series could be trend stationary. So in this case, the time series has a trend, but it's a linear time trend, okay? And there is no stochastic trend, okay? So there is no unit root, because what causes the unit root is the stochastic trend, okay? So when you're trying to identify the unit root, basically what we're trying to do is to identify the presence of a stochastic trend. But you can have two types of trends. You can have a time trend, like a linear time trend, and the stochastic trend. If you only have the time trend, but you don't have the stochastic trend, the series is going to be trend stationary. Because, look, you don't have the stochastic trend, so you don't have the unit root, but you still have a linear time trend, which means that if you detrend the series, it becomes stationary. So what you do, if you want to make the trend stationary variable stationary, you need to detrend it. So you remove the time trend, you remove the linear time trend, and whatever is left is going to be I0. It's going to be stationary, okay? So again, a trend stationary time series becomes stationary after detrending. And when I say detrending, I mean you remove the linear time trend. The third option, which is the most common, but it's not always the case, okay? At least in economics, is that the series is going to be difference stationary, okay? So in this case, the series has a stochastic trend. It could have both. It could have a time trend plus a stochastic trend. But if it has a stochastic trend, it already has a unit root, so it's going to be a unit root process, and it's integrated of order 1. And the only way to make it stationary is to use first differences. Okay? So I know these terms are complicated, but that's how it works in time series. All right. So when you say that something is a unit root process, it's the same as saying it's integrated of order 1. And it means that if you take first differences, it becomes I0, stationary. So those things are synonyms in time series. Look, difference, stationary, stochastic trend, unit root, and integrated of order 1. Those things are synonyms. Okay, one more time. Difference, stationary, stochastic trend, unit root, and I1, integrated of order 1. Those 4 terms are synonyms. Clear? Good. Remember, if I ask you the following, what is the difference between a trend stationary series and a difference stationary series? You have to say the difference is the stochastic trend, because the stochastic trend is what gives the unit root. Okay, so the unit root comes from the stochastic trend. Okay, stationary series and trend stationary series, they do not have a stochastic trend. Is that okay? I know it's confusing, but that's how it works. Okay, so for example, if I ask you, if you have a random walk process, do you have a stochastic trend? The answer is yes. Okay, the random walk process has a stochastic trend, it has a unit root, and it's integrated of order 1. But if you first difference the random walk, then it becomes stationary. Okay, just for you to know, let me quit this presentation. If you go to our Moodle page, I have updated the slides for week 1. So if you click here and you open the file, so let's begin from the start. So the new slides, I think, are 10 and 11. So yeah, this was there before here. Yeah, 10 and 11. These are the 2 new slides that I have introduced. I didn't change anything else at all. I just included, you see, slide number 10 and then slide number 11. So in these 2 slides, I explained to you what I just said. Okay, remember, a trend stationary process has a linear time trend and it has a stationary process around the time trend. Okay, so remember, the stationary process is going to happen around the linear time trend, but a different stationary process, which is the same as a unit root process or I1 process, it has 3 components. It has a linear time trend, maybe. It doesn't necessarily need a time trend, but it's going to have the stationary process, and most importantly, it has a stochastic trend. So what creates the unit root, what creates the integrated process is the stochastic trend, okay? And the stochastic trend is also known as the martingale process, okay? So when you hear things like a martingale process or a martingale series or time series, martingale means stochastic trend, okay? So because those, I don't know why we have so many different terminologies for the same thing. Okay, so but basically that's how it is, folks. I didn't invent this term. So, but when you see things like martingale process, that means a stochastic trend. It means a unit root or integrated of order 1, and that's what creates the permanent effects. Okay. And the stationary process is what creates the transitory effects, okay? Because this component here has mean reversion, okay? The stochastic trend does not have mean reversion. So the difference between the different stationary process and the trend stationary process is the stochastic trend. Okay, it's the martingale process. Because remember, the unit root comes from the stochastic trend. And it makes a lot of difference, okay? When you're doing your model, it makes a lot of difference, especially in terms of forecasting, whether or not you correctly model the stochastic trends, okay? That makes a huge difference. That's why I emphasize this so much. It makes a huge difference. And sometimes it's difficult to know if the series has a stochastic trend or not, okay? And here I have an example. I'm not going to go over this. So please take a look at the slides from week 1 again that I updated, then explain to you, what is actually the connection between the unit root and the stochastic trend. It has to do with this variable here, rho. If rho is 1 or higher than 1, then you have a unit root. But if rho is less than 1, then this becomes stationary, okay? Even though with high persistence, but it's still stationary. Because what we're trying to model is this, ideally. We have 3 possibilities. Okay, well, this is a time series. It can have an explosive response to a shock. It can have a permanent response to a shock, or it can have mean reversion. So the blue line is trend stationary. The green line is unit root, so it has a stochastic trend, so it has a permanent effect. That's ideally, that's what is not ideally, but I mean behind the scenes, that's what is happening. The trend stationary process, it goes back to the trend. The unit root process has a permanent effect. It does not go back to the previous trend, and an explosive process just drifts away permanently. All right, so going back now. Now, if the time series are integrated of order 1, then you can test for contegration. Contegration is just defined as the common time and stochastic trend. So there's a common trend, and this common trend means that you have a stable long-run equilibrium between the variables. That's it, okay? Contegration means you have a common trend, and this trend can be a composite trend of time trend and stochastic trend. But as long as it's a common trend across all the variables, it means that they are self-correcting. So there's a stable long-run equilibrium. And what happens is you have contegration if the residuals from the contegrated regression of I1 variables is stationary. Okay? So when you run a regression, even using OLS, so you have I1 variables, you run the regression, you get the residuals. If the residuals are stationary, then you have contegration, because that means they are self-correcting, and they are self-correcting towards a stable long-run equilibrium. And this stable long-run equilibrium is the common time and stochastic trend. Then you can run your time series model, and you have different options here. You can run the var if your variables are I0, and then you run the grandeur causality tests. But remember, I told you this in my messages, okay, and in my lectures. The var model only works if the variables are stationary, okay? So if you have I1 variables, they have a unit root, they are not contegrated, okay, they are not contegrated. What do you have to do? You need to take first differences. When you take first differences, they become stationary. Then you can run the var model using the differences, because the var model only works if the variables are stationary. If your variables are not stationary, if they are integrated but they are not cointegrated, then you need to take first differences and then run the var model in first differences. Then you can run the grandeur causality tests in first differences. Okay, you need to run the grandeur causality tests with stationary variables. The grandeur causality test only works with stationary variables. So make sure your variables are stationary before you run grandeur causality tests and the var model. Now, if your variables are I1 and they are co-integrated. You have to use the VAC model, and you have to use the Toda Yamamoto causality test. Okay, so the Toda Yamamoto causality test is the same as the Granger causality test, but it's adjusted to integrated variables. Okay, non-stationary variables. You can also use the ARDL model. The difference is that the VAR and the VAC models, it's a system of equations. So it's a system of endogenous variables, and the variables are endogenous to one another. But you also have the possibility of just running a single equation. So the ARDL model has just a single equation. And then within the ARDL model, you can run the PSS bounds test to test for the statistical significance of the long-run effects. And remember, the long-run effects are the permanent effects in the ARDL model, because you have variables in levels, they account for the permanent effects, and you have the variables in first differences, and they account for the temporary short-run effects. And the last option that we saw was the ARIMA model. The ARIMA model cannot ever establish causality. The ARIMA model has only one purpose, which is to do forecasting. Okay, and it only applies it only applies for one single time series at a time. Okay, so the ARIMA model will never be able to to come up with any causal inference. It's only good for forecasting. Just to refresh your mind, we saw 3 unit root tests. We saw the augmented Dickey-Fuller test. We saw the Phillips-Perron test. In both cases, the null hypothesis is that you have a unit root, okay? But it's good to cross-check the results using the KPSS test. And it's a cross-check because the null hypothesis is flipped. So in this case, the null hypothesis is that you don't have a unit root. So basically, we run these 3 tests together because the first 2, they have one null hypothesis, and the KPSS test has the opposite null hypothesis. It's good for cross-checking. So what you do, you look at the p-value, you look at the critical values. So if the p-value is lower than 5%, then you can reject the null hypothesis. Just remember that the tests have different null hypotheses. But there's a problem. And I think you noticed this problem in your project. Okay? The unit root tests and the co-integration tests, okay, this applies to unit root test and co-integration tests. They have low power. When I say low power, I mean low statistical power, okay? So what is low power? So usually the null hypothesis is that you have no significant effect. So that's the negative result. It's like having a negative COVID test. You only see the first stripe, okay? That's the negative result. So you can think this in terms of like this COVID, the lateral flow test. So H0, the null hypothesis is that you don't have COVID, right? So that's the negative test. You get only one stripe. The alternative hypothesis is that you do have COVID. You are infected with COVID. And that's the significant effect. So the result is positive. That's when you have 2 stripes, okay? But remember, the COVID test can have 2 sources of errors. It can have the type 1 error and the type 2 error, right? So you can have a false positive or a false negative. And then how do you know the power of the COVID test? You can do the same in econometrics, okay? It applies to all these cases. The table summarizes the meaning. So probably you remember this from statistics. So type 1 error is the false positive, okay? Is when the test says that you have COVID, but actually you don't. So you are incorrectly rejecting a true null hypothesis, okay? So the test says you have COVID. So you see two stripes, but actually you don't have COVID. So here you are rejecting the null hypothesis, but in fact, the null hypothesis should not be rejected. So what is the problem? The problem is that the p-value is lower than what it should be, okay? And you also have the second type of error, type 2 error. That's the worst problem. It's when you have COVID, but the test shows you only one stripe. So you are infected with, and I saw this with my friends. They told me, because then you do the PCR, and then the PCR test says you have COVID, but the lateral flow test says that you don't have COVID. So you do have COVID, but the lateral flow test says that you don't have it. Okay, so that's a false negative. So you are incorrectly failing to reject a false null hypothesis. Okay, you do have COVID, so you have a positive result in your blood, but the test comes out negative. So it's a false negative. So you don't reject the null hypothesis when there is a significant effect, okay? The problem is that the p-value is higher than what it should be, okay? You should reject the null hypothesis. So you should reject the negative result. So you have a positive result. So you do have COVID, but the test fails, okay? So how do we measure the statistical power of any test? Well, the power of a test is the probability of identifying a true positive, okay? So what do you want? You want a test that says that you have COVID when you actually have COVID, okay? That's what you want. That's the power. So what is the probability of the lateral flow test telling you that you have COVID when actually you have COVID, okay? That's the power of the test. I think for the lateral flow test, it's more than 99%. But in econometrics, it's usually much lower than that, okay? Especially with like unit roots and contegration. It's around like 80%, sometimes lower than 80%. So just imagine this. Imagine that you have like a COVID test that only works like 70% of the time. That's a huge margin of error, okay? And that happens with unit root tests and contegration tests. So it's much worse than a COVID test. And one of the reasons is because you don't have enough data. That's one of the problems with the unit root tests. For example, I'll tell you what is happening this year. So last year, 1 year ago, it was clear that the variables were co-integrated. But we are fetching the data directly from the Federal Reserve System, from the server, the FRED website, right? So R is fetching the data directly. So it means that when you run the code, you're always going to get the most up-to-date data. So when you're doing your project now, you're fetching the data directly from the FED server, which means you're getting the most up-to-date data, which is not the same from last year because the data is monthly and 1 year has gone by. So you have 12 extra months of data, and those 12 extra months, they can make the series which are integrated not to co-integrate. And I think that this is what is happening because last year, I believe the data was co-integrating, but this year it's very ambiguous. So, and what is happening is that the data that was released in the past 12 months is different because we had COVID, we have the war in Ukraine, and those things are affecting the economy at the global level. So when more data is released, you change the nature or the pattern of the data, and then what was co-integrated before might not co-integrate again. You see? So that's why econometrics is difficult, because as more data is released, some results will appear, some results will disappear because you have more data. To summarize, the problem with co-integration and unit root tests is that these tests are very sensitive to the amount of data that you have. So if you don't have enough data, you get one result. As soon as you start to have more data, the result will change. Because these tests, they depend a lot on the size of the sample that you have. So that's it. That's it. So if they have a power of 80%, it means that one-fifth of the time, you're gonna reject something that should not be rejected. But that's how it is, folks. It's the nature. Ideally, we should have like, sorry, we should have like millions of observations, but we don't. Okay, we have like 200, 300, not millions. So that's the nature of econometrics. So remember, the probability of identifying a true positive is the same as the probability of identifying, it's the same as the probability of correctly rejecting a false negative, okay? So what do you want to do? You want to reject a false null hypothesis. That's the power. You want to reject something that is false, okay? So if the null hypothesis is actually false, what is the probability that you're going to reject something that it is in fact false? That's the power of the test, okay? So that's the probability of rejecting the null hypothesis when there is indeed a significant effect, okay? So you want the test to tell you that you have COVID when you actually have COVID, okay? So the statistical power is the probability of a true positive, which is the same as 1 minus the probability of a false negative, which is equal to 1 minus the probability of a type 2 error. So again, unit roots and contegration tests, they have low power. We saw 2 contegration tests. Folks, just 1 second. I need to drink some water here. Just 1 second. I'm speaking too much. We have 2 contegration tests, basically. We have the first ever contegration test, which is the angle grandeur. It's a 2-step procedure. In the first step, you have to run the regression of one variable against the other. So remember, if the variables are integrated, I1, all right, so if you have 2 or more variables that are I1, you can run the regression of one against the others. That's your first step. You just run an OLS regression. Then what do? You save the residuals. Then what do? You're going to run unit root tests on the residuals, okay? If the residuals are I0, if the residuals are stationary, then you can claim contegration, okay? So if you have integrated variables, they're integrated of order 1, you run the regression of one against the other, you check the residuals. If the residuals are stationary, you have contegration. Remember, the critical values for the angle grandeur test are non-standard, so you cannot just run the ADF or PP or KPSS test on the residuals. I mean, you actually run those tests, but then be careful, you're not going to look at the critical values from the ADF test, because the angle grandeur test has its own critical values, okay? They have been tabulated, so just be careful. It's not just like run the ADF test on the residuals and look at the critical values of the ADF test. No, you cannot use the critical values from the ADF test. You have to use the critical values from the angle grandeur test. But don't worry, because the computer does that automatically for you. So when you run these tests like in R already gives you automatically the critical values and the p-values from the angle grandeur tabulation. Remember, these distributions are not standard, and they're not standard because the variables are integrated, okay? I'm going to repeat this. The variables are integrated, they have unit roots, so asymptotically, the distribution of these variables, they do not converge to a standard normal distribution. Even if you normalize the distribution, even if you curve them, they're not going to approach a normal distribution asymptotically, okay? Why? Because they have unit roots. That's what is happening. Integrated variables that have a unit root, asymptotically, their distributions will not approach a standard normal distribution asymptotically. So when you read in the textbook, oh, these variables do not have a standard distribution, or when they say, oh, the estimator has a non-standard distribution, what they're saying is, even if you keep adding more and more data, if you keep adding more data, it means asymptotically, as the sample size grows, the distribution of those variables will not approach a standard normal, even with a lot of data. Okay, why? Because they have a unit root, they are integrated of order 1. So when the variables when they don't have a standard distribution, you must try to find what is their distribution asymptotically, and that's what the angle grandeur table gives you. So the critical values are going to be different. The other option was the Johansen test. The Johansen test, basically, it's a multi-dimensional version of the augmented Dickey-Fuller test. Okay, that's it. It's the multi-dimensional generalization of the ADF unit root test. So in the ADF test, you have the rho stat, which is just a scalar, right? So you're trying to measure rho, and rho tells you if you have a unit root or not. But in multiple dimensions with multiple variables, the rho, which is a scalar, becomes the pi matrix in the Johansen regression. So the most important thing in the Johansen regression is the pi matrix. And just remember, the pi matrix is the multi-dimensional version of the rho statistic in the ADF test. The main innovation in the Johansen procedure is that it's a single-step test that avoids the two-step procedure of the angle grandeur test. We have two statistics. We have the trace test and the eigenvalue test. The null hypothesis for both is that the series are not cointegrated, so R equals 0. Remember, R is the rank of pi. Okay, again, R is the rank of the pi matrix. And R, which is the rank of the pi matrix, gives you the number of cointegrating vectors. Okay? So if R is 0, the series are not cointegrated because the rank of the pi matrix is 0. They do not cointegrate. And so even though the series are integrated, they are not cointegrated. If R is 1, you have one cointegrating vector and so forth. The rule is the following. If you have a 2-time series, you can only have one cointegrating vector. If you have 3-time series, you can only have 2 cointegrating vectors at the maximum. So R is always the number of variables minus 1. Maximum. Okay, so R max, sorry, I should say R max, the maximum R that you should get is the total number of variables that are integrated minus 1. Okay, because integration is between them. Okay, so if you have 5 variables, sorry, I should say 5 integrated variables. If you have 5 integrated variables, then the maximum number of cointegrating vectors will be 4. So the R max will be 4, but the actual R could be 0, it could be 1, could be 2. So again, you have to look at the critical values. You can look at the p-values, and then you can reject the null hypothesis. Now, the ARIMA model. ARIMA stands for autoregression, integration, moving average process. It's a one-variable model, which means that the variable is regressed on itself, on its own past values. The first thing that you got to do is to test for unit roots. You need to test for the presence of integrated processes. If the process is integrated, if it has a unit root, so you're actually estimating the ARIMA model. If there is no unit root, in practice, it's just an ARMA model because the I disappears. The I stands for integration. So if the variable is not integrated, then it's just an ARMA model. The ARIMA model is good for forecasting. It has a close fit to the data. It performs very well, but it's just useless for causality analysis. So if you want to establish causality, the ARIMA model is basically useless. In practice, how do you estimate the ARIMA model? Basically, you have to estimate, let's say, thousands or millions of ARIMA models in practice. The computer does that for you. And then it's going to choose the model that has the lowest information criterion. So you're going to compute, let's say, 1 million ARIMA models. The computer does that for you behind the scenes. It computes the Akaike information criterion, the Bay-Schwartz, the Hanna-Quinn, and then you say, okay, give me the model that has the lowest Bay-Schwartz information criterion. So, and that's the best model, okay? So that's it. The computer is going to calculate, let's say, thousands of different ARIMA specifications. And then you say, okay, give me the one that has the lowest BIC, okay? So the computer does that for you automatically. The residuals from the ARIMA model, they must be well behaved, so no heteroscedasticity, they must be normally distributed, and there must be, of course, no autocorrelation, okay? The first thing that should disappear is autocorrelation. If you have autocorrelation in the errors, the model is not good, okay? Autocorrelation is the first thing that should disappear from the residuals. If you have autocorrelation in the residuals, your model is really not good, okay? And then what do? You can test the power of the forecasts using basically two methods. One is the in-sample forecasting, and the other method is the out-of-sample forecasting, okay? We have done this in the lecture. So basically, either you use the data that you already have to do the in-sample forecasting, or you try to wait until something happens in the world and then you check for the out-of-sample forecast. The second, well, actually it was the first model that we saw, the ARDL model. It stands for autoregression distributed lag model. It has two components. AR is when the dependent variable is regressed on past values of itself, both in terms of levels and in force differences. The distributed lag component is when you have contemporaneous and lagged values of regressors, both in levels and in differences. So basically now we have one dependent variable and one or multiple exogenous variables. Now, the most important thing about the ARDL model, and I love this model, I think it's really interesting. But the thing is, if you want to establish causality, it only works if the regressor is strictly exogenous. Okay, that's one of the requirements of the ARDL model. To be precise, only the strictly exogenous, so it must be exogenous relative to the past, present, and future. So only the strictly exogenous regressors have a causal interpretation. If the regressor is not strictly exogenous, then you can include it in the regression. You can include it in the ARDL model, but it's not going to have a causal interpretation, but it can still be good for forecasting. Okay, you can still do it. Okay, you can use the ARDL model for forecasting, for prediction. That's fine, no problem. You can use the ARDL model for prediction. The thing is, if you want to establish a causal, if you want to do causal inference, if you want to find the causal mechanism, then the regressor has to be strictly exogenous. But as I said, the problem is that at the macroeconomic level, it's almost impossible in time series to find a time series at the macro level that is strictly exogenous. The ARDL model is going to include variables, both in levels and in first differences, and we're going to have contemporaneous and lagged effects. So that's why I like this model, because you can have contemporaneous effects, you can have lagged effects, you can have effect in levels for the long run effects, and you can have the short run effects with the variables in differences. So the regressors in levels, they're going to control for the long run, and long run means permanent. They're going to control for the long run effects. The regressors in differences, they control for the short run, and short run is temporary effects. You can also test for contegration using the Johansen and Engelgranger tests before you estimate the ARDL model. And after you estimate the ARDL model, you can test for the significance of the permanent effect using the PSS bounds test. Okay, so again, the regressors in levels, they control for the permanent effects. The regressors in differences, they control for the temporary effects. Before you run the model, you can test for contegration. After you run the model, you can use the PSS bounds test to test for the statistical significance of the permanent effects, the long-run effects. Now, in practice, what happens is that the ARDL model has a lot of contemporaneous and lagged effects combined, both in levels and in first differences. So when you look at the estimates directly, it's difficult to understand what they mean. And sometimes, and what happens is that the results come with the signs flipped. It's the nature of how the equation is written. So the signs come with the opposite. Sorry, the estimates come with the opposite sign. So the best way to just untangle the meaning of the estimates is to plot the impulse response functions over time. And these impulse response functions, they simulate how the dependent variable responds to exogenous shocks to the regressors. Okay. And again, the residuals have to be well behaved. Okay, no heteroscedasticity. They gotta be normally distributed, and they have to be. They cannot have zero correlation. Okay, so if the residuals are autocorrelated, you need to include more variables, or you need to include more lags, and so forth. You cannot allow the residuals to have autocorrelation, heteroscedasticity, and ideally they should be normally distributed. Now, the VAR model. So the VAR model is a vector model. So it's a vector autoregression. And the difference is that the ARDL model, the ARIMA models, they have only one dependent variable. The VAR model is a vector of dependent variables. So now we can allow for the existence of multiple endogenous variables. And each one of them is going to be regressed on past values of itself. And then it's going to be regressed also on contemporaneous and past values of the other endogenous variables. So it's a system of equations. The main problem with the VAR model, which is actually the most common problem in econometrics, is identification. The structure of the system of equations, it cannot be estimated directly because you do not observe the structure of the system directly. You cannot observe the structural errors directly, and that's the major problem. Okay, why? Because that's the problem of endogeneity. I told you this. Like the biggest problem in econometrics is the endogeneity problem, because most of the time, one variable is always endogenous to the other, and you have reverse causality, and that problem happens with the VAR model too. Because the variables are endogenous, right, to one another. So you can call it the problem of endogeneity, the problem of simultaneity. It's the same stuff. So these endogenous variables, they are determined together simultaneously. One solution, and this is what that's what I was teaching you this semester. The solution is you have to estimate the reduced form VAR. Then you have to use the Cholesky decomposition. Some people call it the triangular decomposition. And you do that to recover the structural errors and the structural VAR. Okay. And then from the Cholesky decomposition, from the VAR, after the Cholesky decomposition, then you plot the impulse response functions to understand how the system responds to exogenous shocks. So remember, the impulse response functions, they come from the structural VAR. okay? And the structural var comes after the Cholesky decomposition. So if you change the Cholesky decomposition, because you have one Cholesky decomposition for each, sorry, you have as many Cholesky decompositions as variables. So if you have two endogenous variables, if you have two endogenous variables, you're going to have two Cholesky decompositions. Okay, so you have as many Cholesky decompositions as endogenous variables. Two endogenous variables, two Cholesky decompositions. If you have 5 endogenous variables, you're going to have 5 Cholesky decompositions. And then the IRFs, the impulse response functions, they are sensitive to the Cholesky decomposition that you have chosen. So if you change the Cholesky decomposition, you might change the impulse response function. It's not a good sign if the impulse response function is changing a lot when you change the Cholesky decomposition. Ideally, when you change the Cholesky decomposition, the impulse response function should not change much, which means you have correctly identified the structural var. But if the IRFs change, if the pattern of the response changes a lot when you change the Cholesky decomposition, then it's not a good sign. Again, the residuals must be well behaved. And one of the limitations is that the var is actually not suitable if you have more than 5 endogenous variables. Because then what is the problem? If you have 5 endogenous variables, you're adding lags of each variable into each equation. Remember, the var is a system in which the lags of the variable itself and the lags of the other variables are included in every single equation. So when you add one more endogenous variable, you add one more equation, and you add a bunch of lags to every single equation in the system. So if you don't have enough data, you end up running out of degrees of freedom very quickly. And as I mentioned before, in the var model, I just need some more water here. In the var model, the variables have to be I0. They have to be stationary. The grandeur causality test does not work if the variables are non-stationary. Why? Because the grandeur causality test is an F-test. Okay, it's an F-test on the joint significance of the lagged regressors. That's what the grandeur causality test. It's a prediction test. Okay, it's not actually causality. Grandeur causality is not causality. Grandeur causality is about prediction. Okay, if past realizations of one variable predict what happens to the other variable, you have grandeur causality. So I think it should be called a grandeur prediction test, not grandeur causality. It's not about causality. It's just prediction. Okay, it's a grandeur prediction test. It's an F-test, and an F-test is always a joint significance test, because remember, the T-test is for the individual significance. If you want to test for the joint significance, you have to use the F-test, okay? So the F-test is a collection of T-tests. And that's what it is. An F-test on the joint significance of the lagged regressors is the grandeur prediction test. Let's say prediction, all right? Officially, it's called grandeur causality test, but I think it's confusing because it's not actually measuring any causality. It's measuring just prediction. And the F-test only works with stationary series. Why? I told you this before, like, I don't know, half an hour ago. The thing is, the T distribution and the F distribution, they are derived from the normal distribution of the variables. But variables that have a unit root, variables that are integrated, they do not have a normal distribution, even asymptotically. Okay, I don't know if this is easy or complicated to you, but what happens is this: the t-test, the f-test, they come from the normality assumption, and that's what we mean by a standard distribution. So if your variable asymptotically reaches the normal distribution, that's fine. But in economics, especially in time series, most series are integrated. They have a unit root, which means that they do not follow the normal distribution. So if they do not follow the normal distribution, the t-tests and the f-tests are useless. The grandeur test is an f-test. So if an f-test is useless, the grandeur test is going to be useless. So the grandeur causality test only works if the variables are stationary. Okay, so unit root tests, sorry, I should have written there, let me put, it's I1, that's what I meant. Unit root I1 series. So unit root I1 series, they don't have standard distributions like T and F, okay? So, but if you want to test for grandeur prediction using non-stationary variables, then you got to use the Yamamoto prediction test. Let's say prediction test. So in the VAR model, the variables cannot be cointegrated. If the variables are cointegrated, then you have to include the error correction term that represents the cointegrating vector. And basically, it means you're estimating the VEC model, okay? And the VEC model is our next model. The VEC model is essentially a VAR model plus the error correction term for cointegration. The error correction term is the cointegrating vector. Remember this. Why do you have to include the EC term? Because the EC term is the cointegration. It is the cointegrating vector. So if the Johansen tests, all right, if they reject the null hypothesis of no cointegration, then you got to include the error correction term in the VAR model, okay? Which means that you're actually estimating the vector error correction, the VEC model, okay? Remember, the cointegration that you found implies that the variables share a common trend. This shared common trend is the stable long-run equilibrium itself between the variables. So cointegration implies a self-correction mechanism that brings the series back into a stable long-run equilibrium. And again, you can do the same as we do in the VAR. You're going to plot the impulse response functions to see how the system responds over time after a shock is given to one of the endogenous variables. Okay, remember, you have to include the EC term because the EC term is the cointegration, okay? It represents the cointegration. But the VEC model has the same problem as the VAR model, which is the identification problem. You cannot observe the structural VEC model directly. You have no access to the structural errors directly. What do you have to do? You have to do the same. You have to estimate the reduced form VEC model. Then you have to use the Cholesky triangular decomposition to recover the structural errors. And again, the impulse response functions are going to be sensitive to the specific ordering of the variables in the Cholesky decomposition. And if you have 5 variables, you're going to have 5 Cholesky decompositions. So yeah, it's the same problem as the VAR, okay? The residuals must be well behaved as before, no surprise there. So let's now move finally to the panel data models. I'm going to compare each model. I'm just drinking some water here. The first question is, why do we need panel data models? Can't we just pull the data? We could just stack the data. Why do we need panel data to begin with? And what do we mean by unobserved effects? Okay. So remember, So panel data sets allow us to control for the heterogeneity across entities. And this heterogeneity across entities can be either statistically significant or not. Okay, so the fact that you have heterogeneity, that you have differences. When I say differences, I mean not differences like in time series. I mean differences in the sense they are not the same, like they are heterogeneous. So like countries, right? So if you have a panel of countries, each country has its own characteristics. All right. So the UK is different from Italy. Italy is essentially different from France. France is very different from the Congo. Congo is very different from Brazil, and Brazil is different from Bolivia, and Bolivia is actually much different from China, and China is very much different from India, and India is super different from Russia, and Russia is very different from the United States, for example. So each country has its own particular characteristics, okay? The question is, those particular characteristics of each country, they're going to be included in the panel data set. The question is, are these differences statistically significant or not? And we have two options. They could be significant or they could be insignificant, okay? If this heterogeneity across entities, if it is statistically significant, then you have to use the panel data approach, okay? But if this heterogeneity across entities is not statistically significant, then you don't have to use panel data. You can just pull the data, you can stack the data, and use the stacked OLS model or the pooled. The official language is the pooled OLS model. And when we say panel data model, actually what we mean is the unobserved effects model. Okay, that's what we actually mean. It's the unobserved effects model. Why? Because a panel data model allows us to control for the individual effects or the time effects. Okay. This is something that I have been studying recently. So there is one caveat here. You either control for individual effects or time effects. Try not to control for both, okay? So if you control for what is called the two-way effect, which means you're controlling for individual plus time effects at the same time, then there's a caveat. And the caveat is that it becomes almost impossible to understand what the estimates mean after you run the model. You can manually run the model, it works, but you're going to get the regression coefficients. And if I ask you, what do they mean? If you have two-way effects, it's going to be actually very difficult for you to explain, and for me to explain what the estimates actually mean, okay? So just remember, if you have to run a fixed effect model, try to run the individual effect only, or the time effect only. Don't include two-way effects. You can actually include it. You can do it, and you include it in the consolidated table. But just remember that when you have two-way effects, it's difficult to understand the meaning of the coefficients. What is the main advantage? What do you gain from using a panel data model? Well, it's because you can control for the unobserved effects, okay? And what is that? Well, unobserved effects are the variables that affect the dependent variable, but we cannot measure them. Either because there is no way to actually measure them, or because the data are not available. Okay, so when you need to include a variable in the regression, but that variable cannot be measured, or it could be measured, but we just don't because we don't have the data, then it's called an unobserved effect. It's something that should be a regressor in the equation. It should be there in the equation. It's not, either because it's impossible to measure it, or because we don't have the data. Sometimes it's too expensive to measure something, and the data are not available. So you have an unobserved effect. So the panel data model is going to help us to partially overcome this problem. Okay. So the first thing that you got to do when you have a panel data set is to test for pullability. Okay. So you're going to test for pullability, which basically means you're testing whether or not you should use a panel model. Okay, so if the data can be stacked, if the data can be pulled, then you are going to use the pooled OLS model. There's no need to use a panel model. But if the data cannot be pulled, which means you have to control for the heterogeneity, then you're going to use the unobserved model for panel data. When the data cannot be pulled, it means that the data set contains heterogeneity among the individuals, okay, among the groups or entities, and that heterogeneity is statistically significant. And because it is statistically significant, you need to control for that heterogeneity, okay? You need to control for that heterogeneity, and that's what the panel model is going to do. You cannot simply discard, you cannot just ignore the individual heterogeneity if it is statistically significant. So the first step in panel data is to test for the pullability of the data. So if the heterogeneity is statistically significant, then you have to use the either fixed effects or random effects. So the individual component needs to be modeled. It needs to be controlled for. And then the second step is to actually estimate one of the unobserved effect model. Okay, so we have many different options. We have the fixed effects models, like with the within estimator, between estimator, first difference estimator. We have the random effect model. We can use instrumental variables like two-stage least squares and GMM, generalized method of moments. So let's see each one of them. And that's the last part of the revision session. I keep drinking more water here because I'm speaking so much. So what the fixed effect is going to do, it's going to include different dummy variables or different intercepts that control for this individual heterogeneity in the data. And these individual intercepts are going to capture the individual fixed effects. So every individual or every group, every entity, every cross-section, it's the same. It's going to have its own intercept, okay, its own dummy variable. And the intercept is going to change according to the group or time or both. And the most important feature of the fixed effect model is that these dummy variables, the individual effects, they are correlated with the regressors. Okay, and in practice, that's what happens. Okay, most of the time, this is exactly what is happening. Okay, the dummy variable is going to change when you change the regressors across countries, for example. So in practice, we do expect this to happen. We do expect the dummy variable to be the individual effect to be correlated with the regressors. And that's the most important assumption of the fixed effect model, the correlation between the regressors and the fixed effects. And just to be clear, I mentioned this before, individual effect means it's an effect that is particular to each entity, and they don't vary over time. Okay, they don't vary over time, because if they do vary over time, they're not fixed. Okay, I don't know if the words are tricky to you, but that's what happens. If countries have features that are particular to each one of them, and they are fixed over time, that's a fixed effect. But if they change over time, they are not fixed. It's not a fixed effect. It's a variable that you should measure. It's a regressor that is not fixed. Okay, so just be careful with this. We are talking about stuff that is particular to each entity, but this particular stuff that is particular to each entity should be fixed over time. For example, I told you, like the color of your skin, your parents, right? So it's fixed for you, like I mean, at least your biological parents. So your biological parents are given to you. Your skin color is given to you. What else? The first language that you learned, it's given to you. Um, those are things that are determined and they don't change, so they are fixed effects. But if something can change, then it's not a fixed effect. If it can change over time, it's not a fixed effect. We also have the time effects, and we can control for them using dummy variables for the years, for example. And those are the effects that affect all individuals at the same time. For example, a major global financial crisis in 2008. So when you have the great financial crisis of 2008, that's a time effect, okay? Or when you have the coronavirus, it's a time effect. Why? Because it's an exogenous shock to all countries together at a specific moment in time. So if you have a panel regression, if you have a panel model, and you have the great financial crisis, or you have the pandemic, the COVID breakout, you need to include time effect. Why? Because the pandemic affects all countries in the same year. So in 2020, every single country on the planet was affected by COVID. That's a time fixed effect. So you include a dummy variable for 2020. The great financial crisis in 2008. Again, you include a dummy variable for 2008. Why? Because it's a global crisis. It affects every country on the planet. So it's a fixed time effect. It's an effect that affects all countries across the board. And what happens is that regressors that are, well, they might not be significant in pooled OLS, can become significant in fixed effects and random effects. Why? Because we are controlling for individual effects and time effects. And of course, the error term, which now is called the idiosyncratic error term, it must be white noise. So no heteroscedasticity, no autocorrelation, and they must be normally distributed. The most common fixed effect estimators are the within estimator, the between estimator, and the first difference. So in the within estimator, when we control for the fixed effects, what we're actually doing in practice, we are averaging the variables over time within each entity. I did the plots in class for you, okay? I showed you. If you go back to my slides, you're going to see how that works. What the computer is doing is to compute the averages over time within each country, okay? And then you run the regression on the transformed variables. And the transformation is you work only with the deviations of the variables from their own time-wise averages within each entity. And because you're taking the averages within each country, for example, within each entity, the only variance that is left is within each entity, because you're working with the variances of the entity relative to its own average, okay? So those are called the within group effects. There's another possibility, which is the between estimator. It does the opposite. It computes the averages, but it computes the averages across cross-sections, not within cross-sections. So the variance that is left is between groups or between entities or between countries. So how do you choose between the within estimator and the between estimator? The question that you need to ask yourself is, what is the variance that I want to model? And most of the time, the answer is you want to model the biggest variance. If you have more variance across countries than within countries, you go for the between estimator. If, on the contrary, you have more variance within countries than between countries, you choose the within estimator. So you go after the biggest source of variance. If you have more variance between countries than within countries, you choose the between estimator. If you have more variance within countries than between countries, you choose the within estimator. So basically, the choice between the between and within estimators is done on the basis of answering the question: what is the biggest source of variance? Is it between countries or within countries? If the answer is the biggest source of variance is between countries, choose the between estimator. If the biggest source of variance is within countries, then you go for the within estimator. Another option is to use the first difference estimator. And what you're going to do is that you're going to take first differences of the data, just like in time series, but now you're in the panel dimension. And you do that because first differencing is going to purge. And when you purge, you're controlling for it, right? So you're purging the individual fixed effects. And the first difference estimator, just like in time series, it's the preferred estimator when the t dimension, when the time dimension is large. Okay, so when you have a lot of data over time, probably in economics, they're going to have unit roots. So if you suspect that you have what is called a long panel, it's long over time, you have a big time dimension, then your variables, especially in macroeconomics, they're going to have unit roots. So you might consider using the first difference estimator, because then you take the first differences of the variables and you run a regression on the first differences of the variables. And the fixed effects are fixed. So if you take the first difference of a fixed effect, it's zero. Remember, the difference of something that is fixed over time is zero. So when you take the first difference, you are basically purging, you are controlling for the fixed effect. Remember this, the fixed effect is a dummy variable. The delta of a dummy variable is zero. So when you take the first difference of a fixed effect, it becomes zero. So it has been purged, it has been controlled for, and that's what the first difference estimator is doing. It's taking first differences, and the first difference of the fixed effect is zero. So you control for the fixed effect. Now the random effects model. The main assumption of the random effects model is that the fixed effects are not correlated with the regressors. Okay, so the individual fixed effects are going to be assumed to be random, and they're going to be placed within the composite error term. Okay, so inside the composite error term, you have the time or group fixed effects. So the individual specific component, which is the unobserved effect, is random, and it's uncorrelated with the regressors. Okay, in practice, random effects requires GLS, generalized least squares, because you have to remove the autocorrelation in the composite error term. Why? Because now the error term is a composite term. It has the fixed effects inside it plus the idiosyncratic error. But if you compute the autocorrelation over time of the composite error term, you're going to find that it's not zero. So you have autocorrelation in the composite error term. Why? Because you have the fixed effects there. And the fixed effect inside the composite error term is what gives you autocorrelation, because you have, it's like a drift. Remember when you have like a random walk with a drift? So that drift inside the composite error term causes autocorrelation in the composite error term. Okay, because that's what we're doing. We're manually putting the individual fixed effect inside the composite error term, and because they're fixed over time, it works just like a constant, but inside the error term, and that creates autocorrelation in the error term over time. So the GLS approach to random effects is to compute the model in 2 steps. So in the first step, we are going to run the model using fixed effects to get the estimate for the row coefficient, and the row coefficient is the correlation between the composite error term over time. Remember, the composite error term is correlated with itself over time. So there is autocorrelation in the composite error term. The correlation in the composite error term over time is the row coefficient. But in order for you to include this autocorrelation, this row coefficient in the regression, in the GLS regression, you need to estimate it because you don't know how much it is. If you knew row from the theory, then you can do everything in one step. Then you don't need GLS. But in practice, you don't know row. So because you don't know row, you need to estimate row. And that's the essence of GLS, generalized least squares. You need to estimate row. Once you have estimated row, you include this estimate into the random effects model. So it's a 2-step procedure. Step 1, you run fixed effects, the fixed effect model. You estimate row. Then once you get this row coefficient estimated, you include it into the GLS equation to do the quasi-demeaning of the variables. Okay, so the GLS works on, we're going to quasi-demean the data using the row coefficients. The row coefficient comes from step 1. That's the GLS approach to random effects. Okay, now the interpretation of the coefficient from random effects is actually very difficult because they include the within entity and between entity effects at the same time, or the between groups and within groups at the same time. And I'm gonna talk more about the interpretation of the coefficients later. Okay, I'm just telling you that in principle, it's difficult to interpret random effects coefficients directly. Okay, because there are many different effects going on at the same time. I'm going to come back to this in the last slide, okay? To show you actually how do we interpret the results. So in practice, you're going to see that most of the time, RE models, random effects models, tend to have regressors that are more statistically significant than the fixed effect models. So the joke is you get more stars, right? Because the stars mean lower p-values, so they're more significant statistically. So the difference between the FE and RE models is that in the random effects model, you get more stars because the p-values are going to be lower. Now, in what conditions should you use random effects? And the answer is when the regressors have low variance. Why? Because variables that have low variance, they're very similar to fixed effects. But in the fixed effect model, the fixed effects are going to disappear. They're going to be washed away. Okay? Remember, anything that is fixed over time is going to disappear in the fixed effect model. Just like the intercepts. Because what you're doing is you're creating the dummy variable for each entity. But once you take that transformation in the data, the fixed effects are going to disappear from the regression because you're working with the transformed variables, and the transformed variable is the variable minus its own average. Well, a constant minus its own average is 0. So the fixed effect disappears. Now imagine that you have a variable that is not quite fixed, but it's almost fixed. So it changes very little over time. If something changes very little over time, it's very similar to a fixed effect. And the closer its change is to 0, the closer this variable is to a fixed effect. which means it has a very low variance over time. It's going to be washed away when you do the fixed effect transformation. So if your regressors change over time, but they change very little over time, then the fixed effect model is not a good option, because they're going to these variables are going to disappear just like the fixed effects. So one option is to use the random effects model. Okay, so in practice, people choose the random effects model when the regressors have low variance. Yeah, and the last sentence says again what I said, because the regressors with low variance, like the individual intercepts, will be purged in the fixed effect models. Now to finish, instrumental variables and two-stage least squares. Just 1 second, I need to drink more water. The more I speak, the more I need to drink here. So, as I mentioned before, endogeneity is a very common problem in econometrics. And endogeneity happens when the regressor is correlated with the error term. That's what endogeneity means. Because if the regressor is correlated with the error term, it means that you have reverse causality, okay? When the regressor is correlated with the error term, that means you have reverse causality, and reverse causality goes from the dependent variable to the regressor. It's just the opposite of what you want to estimate. You want to estimate the effect from the regressor to the dependent variable. But if the regressor is correlated with the error term, you have reverse causality. Causality that goes from the dependent variable to the regressor. Just the opposite of what you're trying to do. That's the simultaneity problem. Or endogeneity problem. So simultaneity or endogeneity are just synonyms. They're the same. Now, if you want to identify causality, the regressor must be exogenous. Ideally, it must be strictly exogenous, okay? But in practice, how do you identify causality when the regressor is endogenous? And that's what you're looking for. Like, you have a variable, you want to establish causality from that variable, but you know it's endogenous. So what do? Well, one solution is to use the two-stage least squares, which implies instrumental variables. The instrumental variable is called an external instrument in this case because it's external to the regression. It's not yet included in the regression. And these instruments, by definition, they need to be highly correlated with the endogenous regressor, and they should not be correlated with the dependent variable. Okay, which means that the effect from the instrumental variable to the dependent variable should happen only indirectly through the endogenous regressor. Okay, if there is a direct effect of the instrumental variable on the dependent variable, then the instrumental variable is not actually an instrumental variable and should be added instead to the regression directly as a new exogenous regressor. That's what I mentioned before, okay? Remember, the instrumental variable has an effect on the dependent variable, but only indirectly, only through the endogenous regressor, okay? If you think that the instrumental variable has a direct effect on the dependent variable, then it's not an instrumental variable, it's a regressor. It's an exogenous regressor. And when you have an instrumental variable, you're going to use the two-stage least squares, and it's a two-stage least squares because it has two stages. So in stage 1, we're going to compute the auxiliary regression, and then in step 2, we're going to compute the main regression. Okay, so in step 1, you have to run the auxiliary regression, and that's when you regress the endogenous regressor on the instrumental variables. And this will generate a predicted value for the endogenous regressor. The predicted value, as I mentioned before, the predicted value is the exogenous. It's the exogenous component of the endogenous regressor, okay? And the residual term is the endogenous component of the endogenous regressor. So you are trying to purge you're trying to remove the endogenous component from the endogenous regressor, such that you're left with the exogenous component of the endogenous regressor. So you want the predicted value, and you want to get rid of the residual term, okay? So in step 2, that's exactly what you're going to do. You go back to run the main regression, you go back to the main regression, that's the regression that you're interested in, and you're going to run it, but you're going to replace the endogenous regressor with its own predicted value that comes from step 1, because the predicted value from the endogenous regressor is the exogenous component of the endogenous regressor, okay? So that's what we're trying to do. You're trying to purge, you're trying to remove, to get rid of the endogenous component. So you want only the exogenous component of the endogenous regressor, and that's given to you by the predicted value from step 1. So you, instead of including the variable itself, which is the endogenous regressor, you're going to include its own predicted value, because that's the exogenous component that is predicted by the instrumental variables. So if you have a good instrumental variable, this good instrumental variable, because it's good, ideally it will purge the endogenous component of the endogenous regressor. So now you are in step 2, you are regressing the dependent variable on the exogenous component of the endogenous regressor. Okay, and that's exactly what you want. Okay, but of course, what happens if you don't have a good instrumental variable? What happens if the instrumental variable is not good? It's weak. So when people say that you have a weak instrument, it means that your instrumental variable is not good, it's not strong enough, and that's the problem of weak instruments. And a weak instrument is when the instrumental variable is not highly correlated with the endogenous regressor. Last option, which is the most common today in econometrics, is to use GMM. And GMM is the most common approach in panel data today, is the most advanced technique. So the GMM approach is an improvement relative to the two-stage least squares approach, because the GMM uses a set of external instruments, just like in two-stage least squares, but it also uses another set of instruments, which are called the internal instruments. And these internal instruments are most of the time just lagged values of the regressors. And you're like, wait a minute, like, why would I use lagged values of the regressors as instruments for themselves? Well, because you have panel data. Panel data means you have cross sections over time, right? Well, the lag of a variable is correlated with the variable, right? And it should affect the dependent variable only through the variable itself. So it satisfies the two conditions of an instrumental variable. So the lag of GDP affects GDP. GDP last year affects GDP today, right? So the lag of a variable is it's a potential good instrument for an endogenous regressor. So that's what GMM is doing. It has the exogenous, it has the external, sorry. So GMM has the external instruments, just like in two-stage least squares, but it also has the internal instruments given by lags of the endogenous regressors. And most of the time, because of the time series component of the panel data, these GMM models are actually dynamic GMM models, because people are going to add lagged values of the dependent variable. So if you see my R code on Moodle, and if you do part B of the project, you're going to see that one of the models is a dynamic GMM model, because you can include lagged values of the dependent variable on the right-hand side, okay, on the right-hand side. So when you do that, when you add lagged values of the dependent variable on the right-hand side as a regressor, you have a dynamic model. And in that case, it's a dynamic GMM model, okay? So if you do part B of the project, you're gonna do that, okay? You're gonna see that you can include a lag of the dependent variable on the right-hand side as a regressor. In essence, it's a dynamic GMM model. So most of the time, people choose the GMM model because you can do that. You can include lags of the regressors, and you can include lags of the dependent variable on the right-hand side. So we have the lagged effect of the dependent variable. We have the lagged effect of the independent variables. We have internal and external instruments that address the endogeneity problem. They purge the endogenous component of the endogenous variables. And if you have good instruments, then the endogenous regressors can have a causal interpretation, okay? You can use GMM for forecasting, there's no problem. But if you want to use the GMM model for causality, to identify causality, then you're going to use, and by the way, that's why most people use GMM. GMM is a model that was developed such that people can identify causality. So if you have good instruments and you can test for the quality of, for example, you have the Sargent test, so you can test for the quality of the instruments, then you can establish causality from the endogenous regressors. Now to finish, so how do you choose the model? So in practice, most empirical studies, they use the within estimator with a fixed effect, individual fixed effect. That's what you get in most studies. Fixed effect with individual effects using the within estimator, or people use the GMM if they want a dynamic model. Very few studies use random effects, even if the Hausmann test suggests that the random effect is preferred. Why? Because the Hausmann test is not a sufficient condition for using random effects. Now, in practice, you should test for the significance of individual effects only or time effects only. Okay, so try to avoid, as I mentioned before, try to avoid including two-way effects, okay? Because if you include individual, you can do that, okay? Mechanically, there's no problem, but it's gonna be difficult to interpret the coefficients, okay? Now, you begin by testing for pullability. You need to test for pullability, so you need to make sure that the unobserved effects are significant, okay? So a panel model like fixed effects, it improves over the pooled OLS. You need to check for heteroscedasticity and autocorrelation in the errors, okay? The residuals gotta be well behaved. You need to test for unit roots, especially if you have a long time dimension in your panel. If you find any evidence of non-stationarity, then you might use the first difference estimator. So you can use panel data with unit roots, but you have to use the first difference estimator to remove the unit roots. And there's something called cross-sectional dependence too, because now you have many cross-sections over time. So it's possible that you have correlation across cross-sections, and you got to test for that too. So when you look at my R code on Moodle, you're going to see that there's a test for cross-sectional dependence, and there's a way to control for that. In GMM models, you can check for the quality of the instruments using the Sargent test. If you don't pass the Sargent test in your GMM model, then you might think about changing the instruments that you have. Now, in most panel models, it's difficult to interpret the coefficient estimates directly, okay? Even more if the model is dynamic, okay, as in GMM. If you have a dynamic GMM model, and you look at the coefficients, it's very difficult to understand what they mean, okay? Because GMM includes complex lagged feedback effects and so forth. And these lagged feedback effects, they represent these interactions between lags of the dependent and independent variables, and you have levels and differences at the same time. So what do you do? Okay, what do you do? Well, the first thing that you do, as usual, you look at the statistical significance of the regressors, the p-values. Then you look at the sign of the regressors to see if they're positive or negative. You look at the quality of the instrumental variables for the endogenous regressors. And then what is suggested in the literature, and I have done this myself in my papers, you check for the economic significance of the regressors, okay? And the idea is that the economic significance is something much more important than statistical significance, okay? Economic significance is defined as the cumulative change in the regressor over time times the long run multiplier, okay? And why is the economic significance so much more important than statistical significance, p-values, okay? P-values can be very deceiving. If you want to know more about this, and I would recommend you to know more about this, you can go to YouTube or search on Google. You can search for this this professor from Michigan. Her name is Deirdre McCloskey. And she became very famous in the 1990s, and until today, she's known globally because she's a strong advocate against p-values. She thinks that economists should not even report p-values in their regressions. So she's a very strong advocate of the idea that p-values are they should not even be reported at all. So we should stop using stars and p-values in our studies, because she says p-values are not meaningful. They are highly dependent on the sample that you have. And what we are actually interested in is not on p-values, but not in p-values. We're not interested in p-values. We're interested in the economic significance. And sometimes she says economic significance, or sometimes she says substantial significance, because her idea is that p-values do not measure substantial significance. They measure what we call statistical significance, but statistical significance does not necessarily imply substantial significance, which is what I'm saying here, using this term here, economic significance. Economic significance is, again, it's the cumulative change in the regressor over time times the long run multiplier. And the idea is that p-values are not enough. It's not a sufficient condition to decide if a regressor is economically significant. So p-values are not a good indication of economic significance. Because we can have what is called high impact, low probability variables that can be mistakenly disregarded as statistically insignificant. And that is a problem, because if something has a very low chance of happening, so it's a low probability variable, but if it happens, it has a huge impact, it's a high impact, low probability event. That event is going to have a low p-value. But if it happens, it has a huge economic consequence, okay? So high impact, low probability events can have huge economic significance, okay, despite a high p-value. And if it has a high p-value, it's not statistically significant, but it has a huge economic significance. So that's the idea that Deirdre McCloskey is advocating here. And I agree with her, and I think we should report both the p-values and the economic significance, because in economics, we do have these events, high impact, low probability events. So think about it, okay? High impact, low probability events. They might turn out to have a very high p-value, so they are statistically insignificant, but if they happen, it has huge economic consequences. And finally, I wish you good luck in the exam. All right. So more than 2 hours of revision. If you have any questions, please type now in the chat. Otherwise, I'm just going to finish the session. Once I finish the session, I'm going to get the file with the recording. I'm going to place the recording on Moodle so you can watch it later if you want. If you can bear hearing my voice for 2 hours again. But that's it, folks. So thank you for watching. I wish you good luck in the exam, good luck in the project. And yeah, let me know if you have any questions. You can also shoot me a message by email. All right, thank you very much and good luck. Bye-bye.